Good morning. Today we are going to cover section 1.4, functions. And functions is something that you guys covered back starting in Algebra 1. And you reviewed it in Algebra 2. So therefore this will seem like just a quick review. You should have your cutouts. Otherwise, you can go ahead and print them from the Google Classroom. Or you can send me an email and I can send them to you directly. Or you can copy them down if you wish. Let's go through the definition first. A function f from a set A to a set B is a relation that assigns to each element x in the set A exactly one element y in the set B. So therefore each x can only be assigned once to y. And the set A is the domain or the several inputs of the function f, and the set B contains the range. Remember, your domain are your x values, your inputs, and your range are your outputs, which are your y values. There are 4 different ways to represent a function: as a map, you can do algebraically, as a table, and graphically. The ones that you guys have usually seen the least are mappings. You guys know algebraically, equations, functions, tables, and graph. So let's go through example number 1. And remember that you can pause the presentation at any time. I know you need time to be able to copy things down. So go ahead and pause it if you need to. It says determine whether the relation represents y as a function of x. The first one, we have a mapping. Remember, in order for it to be a function, each x can only be assigned to one y value. In this case, this x or this set A is assigned to 2 different y's. So therefore, this is not a function. 4 is assigned to 2 different. 4 is assigned to 2 different values. And you can think of this as set A and set B, or you can think of this as your x values and this as your y values. Now remember that this can also be represented as a table. So if you want to think about it as a table, that means that if you plug in a 4, you get a 1. If you plug in a 4, you get a 3. If you plug in a -2, you get a 7. So in this case, you have 2 x values being assigned to the same x value being assigned to 2 different y values. On letter B, when they give you a table of values, it's much easier to see because you notice that -2 is assigned only once, -1, 0, and 1, they all assign only once. So therefore, this one is a function. On letter C, whenever they give you a graph, or in this case just a set of points, we are only wanting to see that each x is being assigned only once. So in this case, -2, it's only been assigned to 1 point. -1 is only being assigned to 1 point. 1 is being assigned to 2 points. It's been assigned to 3, and it's been assigned to -1. So therefore, no, this is not a function. Or you can just say not a function. Make sure to give me a reason why. 1 is assigned to 3 and to -1. Example number 2. Which of the following equations represents y as a function of x? And there's two different ways of thinking about it. In Algebra 2 and in Algebra 1, you guys represented this one as a graph, and then from there you determine whether this was a function or not. In this class, we are going to think of it more of an algebraic aspect. Now, if you know what the graph looks like, it's kind of helpful to determine, but I want you guys to think of it as more in the algebraic sense. Now, in order to determine whether it's a function or not, you want to be able to leave the y by itself. So solve for y. So in this case, y is equal to negative x squared plus 1. And this, every time you plug in a value of x, you are only going to get one y. You will get two values when you plug in, when usually you have a plus or minus, and we'll see that on the next example. So is this a function? Yes. Every time you plug in a value of x, you only get one y. Yes, it's a function. You get one. So it's a little more abstract. For letter B, you want to be able to leave the y by itself to determine if it's a function or not. So I'm going to solve for y. We have y squared is equal to negative x squared plus 8. And I'm going to take the square root on both sides. So therefore y is equal to plus or minus, don't forget your plus or minus, negative x squared plus 8. So in this case, every time you plug in a value for x, you're going to end up with two y's. So for example, if you plug in a 2, if you plug in a 2, 2 squared is 4 minus 2, that's negative 4, plus 8 is 4. So you're going to end up with plus or minus square root of 4, which is 2, plus or minus 2. So therefore, if you plug in a 2, you end up with two y values, one positive 2 and one negative 2. So if you plug in a 2, you end up with two y values, one positive 2 and one negative 2. So therefore, the same x is being assigned to two different y's. So therefore, this is not a function. And sense of the plus or minus, it assigns two values for y every time you plug in an x. Or most of the time they plug in it. And there's a few exceptions, but that's the normal case. Now you can also look at it algebraically, or it's going to be graphically, and if you're going to, if we graph it, if I just go into decimals, and I graph each of the functions, if I type in the first one, x squared plus y is equal to 1, notice that this is a function. You can see it graphically. But if I type in the second one, where we have x squared plus y squared, and all of you guys know that this is an equation of a circle, that would not be a function. Let's continue to example number 3. Function notation. When an equation is used to represent a function, it is convenient to name the function so that I can refer to it easily, so it can be referenced easier. Suppose you give the function a name f, then you can use the following function notation. The input will be x, output will be f of x, and the function will be written like this. So therefore, instead of y will be just the f of x. Same thing that you guys saw last year in algebra 1. And we usually read it as the value of f at x, or most of the time we just say f of x. Example number 3. Let f of x be negative 2x squared minus 3x plus 1. Find each function value. So I need to find f of 2. That means that I'm going to plug in a 2 instead of every x. So just a quick substitution. So equal to negative 2x squared minus 3x plus 1. But now instead of the x, I'm going to replace it with the value of x, which is 2. And I just simplify. So it gives me 2 squared is 4 times negative 2 is negative 8. Minus 6 plus 1. So it'll be negative 14 plus 1 will be negative 13. So f of 2 equal to negative 13. And I need to see the notation. F of 2 is negative 13, which means that this is your x and this is your y value. And we can actually plot the point if you need to. 2 comma negative 13. For letter B, I need to find f of negative 3. Negative 2x squared minus 3x plus 1. And I'm going to plug in a negative 3. And I just simplified. That gives me 9, negative 18, plus 9 plus 1. That gives me 10, negative 18 will give me negative 8. Key concept that you have to remember is that this is your x and that'll be your y. And once again, we can plot it. Negative 3 is your input, negative 8 is your output. Now, whenever we substitute, we can substitute just a t or an x plus 2. It doesn't have to be necessarily a number. And you guys did this when you guys did compositions as well. So I'm plugging in, instead of the x, I'm going to plug in a t. Plus 1. And nothing to simplify, so stay as is. For letter D, instead of each of the x, I'm going to replace it with x plus 2. So I'm going to set up first 2x squared, where this will be x plus 2, minus 3x, x plus 2, plus 1. So go and simplify it and see what you get. And then we can check your answers. So let's see, that gives me -2. Be careful when you multiply x plus 2 squared. That means that will be x plus 2 multiplied by x plus 2. And we're going to multiply it out, distribute property twice, or FOIL it. X squared plus 2x plus 2x plus 4. Combine like terms, x squared plus 4x plus 4. And most of you guys can do it quickly in your head, but some of you guys might be forgetting the 4x. So just be careful. So that gives me x squared plus 4x plus 4 minus 3x minus 6 plus 1. Distribute property. I'll combine those two like terms. Combine like terms again. And that'll be your simplified version. Example number 4. On example number 4, we have, do you guys remember what is the name of this function? You guys covered this in Algebra 2. This is called a piecewise function. Now, when you guys are covering piecewise functions, it's basically just a function that has different domains for each of the components. So we basically have 3 functions within one, or 3 equations, or 3 graphs within one, and each of them take a different part of your domain. So this is your domain. So therefore, this equation will only apply when the values of x are less than or equal to 0. This equation, f of x equal to 2, will only apply when x is greater than 0, but x is less than or equal to 0. Between 0 and 2, x is greater than 0 and x is less than or equal to 2. So between 0 and 2, which includes the 2 but not the 0. And this function applies only when x is greater than 2. So find each function value. Now we are going to come back to the piecewise function once we get to section 1.6. F of -1. I'm going to plug in a -1 into which of those 3 functions. So -1 is less than or equal to 0, so therefore I have to use this function here. So therefore I have to use the -2x minus 3. And I'm going to plug in a -1. That gives me 2 minus 3 will give me -1. F of 4. I'm going to plug in a 4 into which of those 3 functions? This is your x value, that's your domain. So that will apply only when x is greater than 2. That's 4 is greater than 2. I'm going to use this one here. So it gives me 4 minus 2 squared minus 1. 4 minus 2 is 2, square is 4, minus 1 is 3. And try the last one, see what you get for this one here. Which of those 3 equations will you use, and see what your answer is. Excellent. So in this case, 2 is this one here. So 2 applies to, is between 0 and 2. So therefore it will be to the orange because it's equal to 2. It doesn't belong to this one because there's no equal sign. So therefore in this case we just have the value. It's always 2. And that'll be your answer. And the last example for today, we're going to be looking at domains, which can be a challenge when you are looking at this only in the algebraic sense. Whenever we do it graphically, it's much easier, but algebraically it can be challenging for you guys. The domain of a function can be described explicitly, or it can be implied by the expression used to define by the function. So they can actually write it down, or it's actually, we know the domain just by looking at the equation. The implied function is a set of all real numbers for which the expression is valid, is defined. So most domains of the functions we state as all real numbers. And one of the things is that most, not all of them, will be all real numbers, which include the lines, parabolas, cubes, absolute values. There are two common exceptions. The square root of x, which domain will be all the numbers that are greater than 0, and rational functions, which domain will be all real numbers except for x equal to 0. Now be careful because this applies, the domain x is greater than 0 only applies with this when there's only an x inside the square root. And same thing for this one. The domain applies, it's all real numbers except for x equal to 0 whenever they have an x on the denominator. It's going to change slightly whenever we have a number as well, but the concept will be the same. Now if we look at them algebraic graphically, if I look at the domain for a line such as y equal to 2x plus 1, or let's say negative 1/2. One of them, the domain is from negative infinity to positive infinity, because there's a value throughout. Parabolas will be the same. If I have x squared to the power of 2 plus 1, whether it's positive or negative, your domain will be from negative infinity to positive infinity, and we say all real numbers. Once we get to the square root of x, notice that your domain starts at 0 all the way to the right, so all the numbers are greater or equal to 0. And yes, if you guys should be equal as well. And for 1 over x, you guys looked at rational equations. So your domain are all the values to the left and to the right except for 0, because once you plug in 0, you end up with a error, or basically we talk about, you asymptote, we talk about undefined. So, and this should be an equal sign. And so just make sure they change it back to an equal sign. So let's go through example number 5. Find the domain of each function. Now whenever they give you a set of points, your domain are your x values. So therefore, your domain, we're going to write it down as a set. So these little braces will be -3, comma, -1, comma, 0, comma, 2, comma, and 4. So whenever it's giving you a set of points, it's a very quick process. You saw that back in Algebra 1. Once we get to an equation, if they give you a graph, you guys are very good at this. But now, the way you want to think about it is, what values can I plug in for x? What is the smallest value that I can plug in for x? We know that with radical functions, your domain will be restricted. So what is the smallest value that can plug in for x? Because you cannot take the square root of a negative number. So you can think that x minus 4 has to be greater or equal to 0. So therefore x has to be greater or equal to 4. So you want to think about the inside number has to be always greater or equal to 0. So therefore your domain will be all the numbers that are greater or equal to 4. And how about whenever we have a rational equation? We know that your denominator cannot be 0. So you'll be all real numbers except for when your denominator is 0. So therefore x plus 5 cannot be equal to 0. So therefore x cannot be equal to negative 5. So your domain will be all real numbers. And you can just give me the r if you want, or you can write down the entire real numbers except when x equal to negative 5. And then your homework is posted on Google Classroom. Send me an email if you have any questions, and I'll see you guys next time. Have a great day.